So let's just start with chapter 3. So what we do in chapter 3, we basically want to hit a few, say, details. So we do have the idea. We know how we can do the training. What is the SGD loop for training? Things like that. We do know it. But in practice, what we use is a tiny bit of advancement to them, right? And what we want to talk about today is in this chapter is that. So we are going to talk about a few tricks that is going to just make your neural networks to work, because if you're imagining that you're just doing everything from scratch, so you don't want to use the SGD implemented by PyTorch, you want to just do it by yourself. When you implement it, like the old days, then it's not going to immediately work, right? And people have come up with lots of trouble, so this is what they have come with many different solutions. Things that I want to talk about in particular in this part are these 4 different things. So the first one is that we want to talk a bit more about optimizers, right? So the optimizers, we talked about SGD, but SGD is like in the vanilla form that we had is not the best thing you can use. You probably have heard of optimizers like Atom, right? Like you always use Atom. Or even when you use SGD in your PyTorch, you're not actually using the very basic one, right? You're sometimes you are adding some momentum to it, which we want to understand what are those parameters. So the first thing is optimizers. Again, in optimizers, like what we did in the backpropagation and other things, I want you to understand what are the components there, how they work. I do know that at the end of the day you can use Atom, but there is the whole world of difference, Atom in PyTorch, but there is the whole world of difference that you just call opt.atom in PyTorch and you don't know what is happening, or you do know what is every single thing inside that, and if you see a trouble there, you can open up the source and see where you can fix it, right? So these are the things that we want to talk in this part. The other one is the idea of hyperparameter tuning and regularization in general. So we are going to talk about this idea that your model can get overfit, like it gets too much fit to your data, that is stops to get generalized on the new data. What is that proper behavior, how we can resolve it? Here we're going to talk about regularization. In particular, we are going to talk about dropout, which is a very well-known regularization. Again, you use it all the time in your implementations, but this is a very important thing to understand why it works and how it works, right? And the next one is about the data preprocessing. So this is a quite simple part, but I want to give you a bit of idea about how people think about data, given that you already have a bit played with this SGD, the estimator that you're computing, sample level, gradient computation, you're going to get a better idea about data processing. So how do you think about data? Like, I do know one image is a bunch of pixels, but if I think of this image as one object, how I think that this object is coming, how I can describe the difference between one image and another, things like that, right? So we're going to get into a bit of data preprocessing part here. And finally, we are going to talk about some tricks. In particular, we are going to talk about batch normalization. This is something that is very crucial when you want to just make your training loop stable, right? Because in assignment 1, last assignment, when you do the classification, the pattern, you just recognize pattern X, you see that there is difference whether you use 0 to 255 or you use 0, 1, right? And this is what is motivating for this part. We are going to talk about that as well. So that's it. So let's start with the first one, which is about the optimizers. So one thing that we want to get back again to the optimization. So this is basically what we did in chapter 1. In chapter 1, we wanted to solve that optimization. And we just talked about the gradient, its properties, and we ended up with gradient descent, right? At that point of time, you thought, OK, I'm going to compute the gradient, right? But now you do know that you are not going to compute the gradient itself. You're computing an estimate of that, right? A noisy version of that. And now the question is that, can I simply go ahead and use that noisy one as the way we talked about in stochastic gradient descent? Or are there ways to improve this estimate that we're taking? So here I have given you a bunch of numbers. So this is for assignment 2, which I'm going, by the way, to upload tonight. So you're going to get some MLP here. And then when you just check, you're going to see you have so many entries there. If you want to just do the optimization, like it's going to be, there's a bit of discussion. You're going to see it there. So at the end of the day, as we talked before, all the time you are using gradient descent, you are computing a gradient, but what you know right now is that this gradient, this blue gradient, is not exactly computed. You are eventually computing an average, an estimate of that, right? A bit of an approximation of it, close to it, but not always very close, right? So you're computing that, and the best thing you can do is to just use a stochastic gradient descent. Now, how we can see if the one, like a stochastic gradient descent with one specific batch size, is a good optimizer or not? How we can evaluate the goodness or the wellness of one optimizer? How we can define it? Well, the question is that how fast the optimizer is going to just get into your minimizer, right? So this is the first thing that you want to know. And this is what we call it the speed of convergence for your optimizer. So the optimizer or the optimization algorithm that you use is going to get towards the minimum point, which is next to it, or the best achievable minimum point around it, with some speed. It means some number of iterations, right? You need to do a specific number of iterations till you get there. And the faster it gets, the lower number of iterations it needs, the faster is the speed of convergence, right? So the way that we define it in theory is what we call optimality gap. And this optimality gap is basically defined as the difference between the loss that we get and the optimal loss that we are looking for, right? Now, this definition might be a bit like too dry for you because you have like just a bunch of formulas here, but maybe this image is going to give you a better idea. So what is, at the end of the day, you have a loss function, right? That loss function is actually the loss of your model, the difference between your model and the true label, right? And now this loss function is a function of variables, right? So here I have W. This W means weight, but by now you do know that we do not have a single weight, right? We have a giant number of weights, but it's impossible for me to show it, so I'm just considering one weight, right? Now, at the end of the day, what you do, you start from one random point, and then you start going down, right? By gradient descent, right? Of course, you are not going really down. You are just going randomly down, right? But hopefully, you are going down enough that eventually you get to the point. What you want to get at the end of the day is the next guy in front of you, which is in the valley, right? The next guy, the next minimum close to you. Of course, there are lots of them around you, but probably there is one of them which is the best achievable one, and then you are moving towards that, right? Now, what is the optimality gap? If you are in one particular iteration, then the difference between the value of the loss you have in that iteration and the asymptotic one, the one which you get after like billions of iterations, this difference is what we call it optimality gap, right? So you would say, okay, if I start, my algorithm is gradually going down. I mean, not necessarily going always down, maybe a bit up, down, but in average it's going down, right? Now, if I keep on doing my algorithm, it's going to just take a long time, and then it arrives at the minimum, right? And then what is the value of the loss at that minimum, right? Now, I'm going to say the optimality gap in every single iteration is the difference between what I was in that iteration as compared to that minimum, right? So now, what do you want in practice? In practice, you want your optimality gap to shrink, right? So you want every single iteration that you are going forward, your distance to the optimal value is less, right? You are closer to that one. So you want this optimality gap, if you start like this, Next step, it goes lower, lower, lower. And eventually, at some good few number of iterations, you end up being at the minimum point, right? So what you want your next iteration, in the next iteration, the gap between where you are and the optimal point be smaller as compared to this one, right? So, and this is also smaller than the previous one and so on. So you start a random point, which is far, far away from the optimal loss, but gradually you go down till you get to the optimal loss, right? This is what you want, right? Now, this is going to happen when you use any optimizer. There is no problem with that. But the question is that how fast you are jumping from this point to the point close to the optimal point, right? Do you need 10 iterations? Do you need 100 iterations? Do you need billions of iterations? You don't know, right? That is the one which is depending on your algorithm, and this is what we call it the convergence speed, right, intuitively. So the speed of convergence is the amount of time you need to get from a randomly started point W0 to a point very close to this W star, right? This is the amount of time that you spend, and that is proportional to the, or reversely proportional to your convergence speed. Everybody's clear? Okay. Now, what is the ideal case? The ideal case is this one. What is the ideal thing you can think of is that every iteration I do, my optimality gap is shrinking by a constant factor smaller than 1. Like now, whatever my optimality gap is, I don't care. Next iteration, I'm going to be 90% of this gap, right? The next iteration, I am 90% of the previous iteration, right? The third next iteration, I am 90% of the second next iteration, yeah? So every iteration I do, I'm getting smaller, right? I don't care what is this alpha. It could be 0.99999, but you know that even 0.99999, when I do it multiple iterations, this is going to shrink, right? Because it's going to be that number, that alpha, to power 2, 3, 4, and so on. And eventually, for some finite number of value of exponent, this is going to be extremely small, right? So this is the ideal case. The best case you can think of, a bit of spoiling is not going to happen in practice, right? This is not what you get, right? But this is like the ideal case. Now, why this is ideal, say that I am in particular iteration t, right? In iteration t, I am alpha optimality gap in the previous iteration, right? In the previous iteration, I was alpha times optimality gap in the second previous iteration, right? So I can write it down as alpha times iteration t minus 2, right? And I can keep going like this, right? So this is going to be alpha squared as compared to the second previous iteration, and so on. If I compare it to iteration 0, the very first point that I started with, this is going to be alpha t, right? Makes sense. You started with one big gap, maybe. Next time you get alpha smaller. The second iteration, you got alpha squared, alpha cubed, and so on. You went down, right? So in iteration t, you are alpha to power t, and you can see that it doesn't matter what this alpha is, right? Even if it is very close to 1, but it's still smaller than 1, you don't really need a very large t till this whole term here get very small, right? So what I can say that if I start with c, and this c is, I don't care about that. It could be giant. Like I can start from a very bad point, right? Very different, high optimality gap at that point. But even if any large c that I put here, at the end of the day, it's going to be c alpha t, and this c is not going to impact at all in terms of the time. The only thing that matters is alpha, right? So if I have this alpha, then the order that I am dropping with is alpha to power t, right? And this is the best order you can think of, because this is exponential drop, right? This is the fastest kind of drop you can get in practice, right? Everybody's clear? Okay, so your optimality gap in time t is going to be of this order. Now, what does it mean in terms of this speed? Well, you can do a tiny bit of math, right? So let's just put it right down like this. So c to power alpha t is the gap I have in iteration t, right? So I started with c, then it was c alpha squared, and so on. I'm in iteration t. Now this is c times alpha to power t, right? Now, typically what I say, I do not say that I want to exactly see the optimal point. I want to get in the neighborhood of that point, right? I want to get around it, right? This means that I want to get like epsilon close to that point, right? I want my loss to be at most epsilon different with the optimal loss that I can think of, right? So if you want that, then this means that this gap, you want it to be smaller than epsilon, right? Now, can you do math for me? How much t I need? So I think you can do it, but sometimes people get a bit confused because log is involved there. So let me just take it off. So I want this to happen. I want this c alpha t to be smaller than epsilon. Can you tell me what should be t? T should be more than something, right? So when I want this guy to be smaller, so this means c alpha t needs to be smaller than or equal by epsilon, right? So this means that alpha to power t should be smaller than equal by epsilon divided by c, right? If I take logarithm from both sides, anything changes? No, right? So I can take logarithm. If I take logarithm, what's going to happen here? T log alpha, right? And then this is logarithm of epsilon divided by c, right? Now, what is logarithm of alpha? Is it positive or negative? Negative, right? Because it's smaller than 1. If I divide everything by log alpha, what's going to happen to this? You're going to get greater or equal, right? So you're going to get greater or equal 1 over log of alpha, that one, right? You see it, right? Everybody's clear? Right? Now, this guy is negative, right? Now, log, if I want to just multiply that with a negative, I put absolute value here, and I keep the negative here, right? If I multiply, if it becomes minus log of epsilon over c, it's going to be log c over epsilon, right? It's going to be log c over epsilon, right? Clear? Now, this log of epsilon absolute value is some number, right? I don't care about that. This log of this c, again, one constant. The only thing that matters here is for me epsilon, because epsilon is the thing that I was fixing, right? I told you I want this epsilon, I want to get this close. Now you would tell me that, well, you need log 1 over epsilon amount of time, probably multiply with something to get there, right? Everybody's clear? So you can just do the math as I did, and then what you end up with is this one, right? That you're going to see that your t should be more than log of 1 over epsilon plus log c divided by that one. This log c, log 1 over epsilon, we do not care about them, right? There are some values, 10, 8, 9, you don't care, right? At the end of the day, the thing that is mattering here is log of 1 over epsilon, right? Now, this means that the amount of time you need is proportional to the exponent, negative exponent of your epsilon. If you want to get 10 to the power minus 3 close to your optimal point, you need your time to be scaled by factor 3. If you want 10 to the power minus 5, this is going to get scaled by 5, right? Everybody's clear? So this is a great speed, like the fastest speed you can think of in practice. And this is what we call it linear convergence, right? The name is a bit counterintuitive, but the linear here comes from the fact that it is linearly proportional to the exponent of epsilon. Because epsilon is always 10 to the power minus something, right? And this is linearly related to that one, right? So you get linearly scaled by that one. If you want to just get from 10 to power minus 3 to 10 to power minus 10, then you just need to double, right? Amount of time that you need, which is a great thing, right? So 10 to power minus 5 to 10 to power minus 10 is a huge difference, right? When you think about this from the accuracy point of view. So this is what we call it the kind of optimizer with linear convergence speed. And this means that your amount of time you need to spend to get close to your optimal point, or epsilon close to the optimal point, is proportional to the exponent of that epsilon, right? Linearly. But what you get in practice, of course, as I said, this is not going to be the case, right? This is the very ideal case. In practice, this is not happening, right? Just think about a real SGD. You're not really dropping every time, right? You're just going half of the times up a bit, and then you go down, up, down, right? And you can never say that you really are dropping with a fixed factor every single time, okay? So this is not really happening. What is happening in practice is this guy. Well, where does it come from? You need to do a bit of math, okay? It's a bit more than a bit of math, okay? So like you need to read the papers that concluded this, right? But at the end of the day, they could show that this difference, and of course you can guess that this difference comes with some sort of expectation, right? The average difference that you're going to get in every single iteration is going to be proportional to this term, right? Now, what are guys in this term? You don't care about L. Eta is, of course, learning rate, but again, you don't really need to care about it right now. The thing that you need to care about is T, right? What is happening here is that your optimality is dropping by 1 over T, right? It's not dropping with some small number to power T. It's dropping by 1 over T, right? It's still dropping. That's fine. This is what I told you initially. You use SGD, you're still going there, right? But this is a huge difference. This is linear drop. That one was exponential drop, right? Uncomparable. Now, just to make it clear for you, what do I mean by that? So, considering this one, right? Some people might tell me, okay, this is still dropping, right? So I just need to give it time. But this give it time is much, much more as compared to linear convergence. When your gap is proportional to 1 over T, how would be the amount of time you need to spend to get epsilon close? Again, you do the same thing that I did before, right? So you would say 1 over T should be more than smaller than epsilon, right? This means T should be more than 1 over epsilon, right? So what you would say the amount of time you need to spend to get close to your optimal point is 1 over the factor of closeness you're talking about, right? Now, this is a huge difference. Just think of, this is sublinear convergence. This is, this is in practice what we get, but this is far worse than what we could think of in the ideal case. Why? Just think about the case where you have your epsilon 10 to power minus 3. In the case of linear convergence, your time is going to get scaled by 3. Here, your time is getting scaled by 1,000, right? If you want to get to 10 to power minus 10, in the linear case, your time is getting scaled by 10, right? Here, your time is scaled by 10 to power 10. Forget about it, right? You can never get there, right? So this is a huge difference in the amount of time you need to spend to get close to the optimal point. Yes? Yes, but you don't really need to care about L here. L is the Lipschitz factor of your function. So it somehow says how smooth your function is. If your function is just crazy going up and down, then that L is getting larger.
What if L increases more than T?
It cannot. I mean, L is a fixed number.
Okay.
Your function is L Lipschitz. This means that its variation is going to be bounded by L. So L is the maximum number you can think of, like in the Lipschitz continuity. But this is somehow like is a kind of advanced version of your function being differentiable. Right? So it does not have edge, but it could just be very picky. Right? And that pickiness, like it's going to take you to this spike where the derivative is not as more than L. So this L is not changing. This is fixed. We cannot change by time. Like, it's a property of the function you are optimizing. Yeah. Okay, questions? No question? Okay, so moral of the story that I wanted to tell you here is that, well, if you want to use a stochastic gradient descent, that sublinear thing I showed you is the best you can get, and this is not a very good thing, right? Now, can we do anything about that? Well, yes and no, right? We cannot really change the order significantly, and the main reason is that, I mean, this is what it is in the real world, right? You never get the ideal things. But the key other thing that it says is that it's going to now be very crucial to be as efficient as possible, right? So I told you here that if you want to get 10 to the power minus 3 close to your optimal point, then your time is going to get a scale by factor 1,000, right? Correct? Now, your time is getting a scale by factor 1,000. This means that the time is very important now, right? If your time is 1 second, it's 1,000 seconds. If it's 1 hour, it's going to be 1,000 hours, right? These are two different things. Whereas in the case of 3, it does not impact, right? I know 3 seconds is more than significantly less than 3 hours, but we can still handle 3 hours, right? But 3,000 hours is something else, right? So because of this sublinearity, we are very accurate about the design of the algorithm or optimizer to get a kind of efficient behavior. And because of that, the vanilla gradient descent that we talked about before is not the one which we use usually in practice, because for that one, that time that I talked about is quite bad, right? So it means that like the basic time to get converge is 1,000 times a big number, right? And the thing that we want to do, we want to reduce that big number, right? And how we can do it, there are a bunch of approaches that we can do. Most simple one is to just do learning rate scheduling, right? If you choose right learning rate in every single iteration, then eventually you can improve the convergence speed, right? So it means that every step you're taking, you're somehow choosing a right step size. And because of that, the average time is getting smaller. You're still seeing 1,000 that average time, but when that guy is smaller, you see smaller time end to end, right? So this is one thing that we can do. The other idea is to improve our gradient estimation by the values that we are obtaining through time. This is the idea of moving average or momentum that we are going to talk about next. The next one is to just add a sort of dimension-dependent update to the learning rate. This is the idea of RProp, and is a kind of basic idea, but it works. So it somehow automatically tune the learning rate in every single dimension. Based on that, based on these two ideas, two different ideas came out. So one of them was RMSprop, which was initially just developed as a kind of extension to this one in the lecture notes of Geoffrey Hinton. And then out of that, we had the Adam algorithm, which is the one which you use right now. Okay? So we are going to talk about them. As I said, we're not going to just open up every single detail, but we get the idea what the momentum is, how you can include it inside your optimizer instead of the basic gradient, or what the RProp does and how you can incorporate it into your momentum update, which is going to end you up with Adam. Okay? Everybody's clear?